All right, now in this video covers section 4.5. In section 4.5, we're looking at trying to think about what an inequality in two variables would look like. Okay, so let me just go to a new page for a second and get you to think about, okay, do you remember we did problems like, 2x minus 5 is less than 13. We did a problem like that earlier, or might have had something like, x plus 7 is greater than or equal to 2. These were inequalities in one variable, in just one variable. Okay, these were in section 2.8. So you did things like, added 5 and then divided by 2. And the issue was that if you had to divide by a negative number down here, you would have to reverse the inequality. And then the other issue was that you would have to graph the solution set. It was one variable, so you were graphing it on a number line. And so you had to think about that key number 9. Let me just put some numbers on either side of that. And you had to show someone that you understood what the solutions to this were, because it's not just a single number. It's any number that's less than 9. And so you shaded to the left of 9. And then on 9 itself, you had to indicate whether 9 was part of the solution or not. And so it's not part of the solution. So you used an open circle. And then we also talked about interval notation. And so for interval notation, you take the left side of the shaded region, you take the right side of the shaded region, and we put a parenthesis on the 9 because it is not part of the solution. We always put parentheses on our infinities. So do you kind of remember doing that, where you had to shade one side or the other on the number line, and then you had to make the decision about an open versus a closed circle? And so the open circle was used, you used an open circle when you had just a less than or a greater than. You used a closed circle, filled in circle, if you had the or equal to underneath it, because that meant you were allowed to be equal. So like after we subtract 7 and get x is greater than or equal to negative 5, when you graph that one, you had to decide which side to shade. It would be to the right because your solutions are bigger than negative 5. But because it said or equal to, you put a closed dot on the negative 5. So you had negative 5 all the way to infinity being your solution, and negative 5 was included. So you put a bracket on it. All right, so what we're doing, what we're about to do is related to that, except for we have both an x and a y. And so instead of it being graphed on a number line, it'll be graphed in a coordinate plane. And so you'll be doing things like y is greater than 2x minus 5 or something like that. Or y is less than 2x minus 5, stuff like that. I'll do it so it has the same. And so what'll happen is you'll graph the line. Okay, and so the line, and then you'll decide based on this whether to make it dashed. This one would be dashed because it doesn't have the or equal to. So the dash is like the open circle. And then you'll have to, again, decide which side to shade. So you just pick a point that's not on the line. And if it works, you shade that side. Okay. If it doesn't work, you shade the other. Okay. And so we'll have to talk about getting the line graphed, deciding whether it's dashed or solid, which is like open circle versus closed circle. It's like for the same reason. So like if you had y is greater than or equal to, x plus 2, something like that, that line would look like this and be solid because of the or equal to. And then you would decide which side to shade. It'd be over here, and we'll talk about why. But that's the gist of it. We're going to have to graph the boundary, which is, in this case, the boundary was just a point. Then decide which side to shade, just like we did here, had to decide which side to shade. And on the boundary, you have to decide whether it's included or not, open versus closed. So we're going to have to find the boundary, decide whether it's included, which would be solid, or not, which would be dashed. And then we have to decide which side to shade. So it's related to what you did before, but it'll feel quite different, okay? I also want to, on this sheet, I also have it where we're relating it back to what you did in section 4.1. This is 4.1, solving by graphing. Okay, so let's go ahead. This first page, I'm going to do a video on the first page, which is kind of the overview of the idea, and then I'll do some videos on the additional problems. Okay, and I may just do the overview video, and then we'll do the additional problems together in class on Thursday. Okay, so if you're going to solve a system of equations by graphing, that's actually section 4.1. You just graph each equation however you're comfortable graphing it. So when I go to graph y equals negative 2x plus 1, I might want to find ordered pairs that are solutions to that equation. The easiest thing would be to plug in x values in and then just work out the y value. When I plug in a 0, negative 2 times 0 plus 1 would be 1. When I plug in 1, negative 2 times 1 plus 1 would be negative 1. Hold on a second. I may be overloading this. Let me see if I can turn off some of this stuff. Not sure what it's doing. Maybe it was trying to save. Let's see if it's back. Okay, I think it's going to let me do it. There we go. Okay, I think it was just trying to save, and I've got a lot of stuff on here now, so it's getting bogged down. Anyway, negative 2 times 1 would be negative 2, plus 1 would be negative 1. If I put a negative 1 in, I'd have negative 2 times negative 1. See, I'm plugging it in for the x. Negative 2 times negative 1 would be positive 2 plus 1 would be 3. So negative 1, 3, 0, 1, 1, negative 1. Now, some of you learn to really like using the slope. So some of you would have graphed by saying the slope is negative 2 and the b value is 1, and just starting at 1 and going down 2 and to the right 1. That's an alternative way to graph, and that's just as good. Okay, so let me get this graphed. This is a 4.1 question, so we don't have to worry about that dash versus solid. You're just graphing the line, and that's the first line. Okay, now the other one, let me do it in blue, that I'm graphing is 3x minus 2y equals 12. So I'm going to graph that one by finding some ordered pairs, and I think I'll use intercepts when I do that one. I'm going to put a 0 in for x. When I do, 3 times 0 would be 0. I can't really write it. Let me move that over a little bit. Okay. When I put a 0 in for x, I'd get 3 times 0 minus 2y equals 12. So when I divide both sides by negative 2, do you see how y would be negative 6? Then I'm going to put the 0 in for the y, and I'll have 3x minus 2 times 0 equals 12, and so x would be 4. You'll definitely have an easier time with this whole section if you're pretty good at graphing lines already. All right, so 0, negative 6 goes off this just a tad, but I'm going to use it anyway. And then 4, 0 would be right here. Okay, and so I'm going to go ahead and draw the line representing that. Okay, so it should look something like that. Okay. All right, now my job is to find the point of intersection. So I'm solving by graphing. This graph is not the answer. The answer to the question is that point of intersection. It appears to be 2, negative 3. 2, -3. So what you should do if you're solving by graphing is plug it in and make sure that it works in both. And if you were to do that, it would. And so that right there would be the answer to the question. And we just use graphing to find it. Okay. All right. Now, that's what you kind of already have been doing. Now, look at these other, make it smaller so you can see them. Look at these other 3 questions. These are related. Notice all I did was take the same equation that we had in number 1, but I put a greater than instead of an equal sign. Number 3, I took the same equation we had in number 2, but I put a less than or equal to instead of an equal sign. And then in number 4, I put the equation number from 2 and the inequality from 2 and the inequality from 3 into one problem. I did that so that we don't have to be bogged down on the graphing of the line because we've already done it in both instances. Okay? So we can focus on the new idea. What do you do with the inequalities? Okay? All right, so on this one, the inequality symbol is a greater than. On these problems, what you do first always is, regardless of what kind of inequality you have, you always graph the line y equals -2x plus 1. So you would do what we did to graph it in problem number 1. So this would take typically longer than I'm taking right now, but we've already graphed it, so I don't have to take a lot of time with it. I already know what it's going to look like. So that's the first thing you do. You graph the line, okay? Then you have to decide whether it's dashed or solid. Since it's a greater than without an or equal to on it, then you know it's going to be dashed. So after I get where my line should be, I think about that, and then I know it should be dashed. Dashed means the points on the line won't work in the inequality, but things right close to the line will. Okay? So that's the first thing you do, is just graph the line and think about whether it should be dashed or solid. All right, then, and I'll call that A. All right, then the next thing I do, part B, is going to be to decide the shading. So what you're going to do is pick a point that's not on the line, just that's clearly not on the line, and pick something that you're not going to mess up with your positives and negatives. So I could pick any point. Maybe I'll pick this guy, the point 2, 1. All right, so I'm going to go to the inequality, right? I'm going to go to y is greater than -2x plus 1. And in place of the x, I'm putting a 2. Place of the y, I'm putting a 1, and I'm asking whether that's true or not. Is that a solution? Does that work? So what I notice is that 1 is all I have on the left. On the right-hand side, I have -4 plus 1, which would be -3. So you're being asked to determine if that's true or not. So 1 is 1 greater than -3? Well, yes, it is. 1 is greater than -3. So this is a solution. So you're trying to decide whether the solutions, which side of the line you just graphed, contain the solutions. And what I just found is the solutions would have to be over here because the point 2, 1 makes the inequality true. So that point has to be on the side that contains the solutions. So the dashed line is like an open circle, and then you're just shading the appropriate side. And you're using, they call it using a test point. So what I did is I test a point. I tested the point 2, 1 to see if it's a solution. Since it was, I shaded the side that contained it. If it weren't a solution, I would have just shaded the other side. Okay. All right, so now let me go on and look at problem number 3. All right, so we've already graphed the line, so our focus can be on the inequality and how to handle that. Notice it has the or equal to on it. So that means when I graph this, it's going to be solid when I graph the line. Part A is going to be to graph the line. 3x minus 2y equals 12. So let me go ahead and do that. We already know, we've already graphed. We know it's going to cross the x-axis at 4 and the y-axis at a -6. And then it has the or equal to on the inequality, so the points on the line are part of the solution. So I'm making it a solid line, not dashed. You'll have an option when you do this. There'll be a tool where you can switch from solid to dashed, depending upon what you need. Okay, after you do that, you're going to test a point to see if it's a solution. It can be any point that's not on the line. You know, I might choose this point. That's an easy one to plug in, the point 0, 0. So if I'm testing 0, 0, I'd plug 0 in for x, 0 in for y, and I'm seeing whether it makes the inequality true or not. So I'm asking that question. But if I put a 0 in for both x and y, I'd get 0. And then I'm being asked, is 0 less than 12? Okay. And my answer would be yes, 0 is less than 12. So 0, 0 worked. This is a solution. So I'm going to shade the side that contains 0, 0. So that would be the graph of the solution set. So you can't just list the solution like you can on question number 1. On number 1, this is the solution. On number 3, the solution would be all the points in the shaded region and all the points on the line. In question number 2, what you see in red is the solution, the shaded region, and then the points on the line don't work. So they're not included. But everything really close to the line from that side would. All right, now what we're doing on 4 is we're putting those two graphs we just did, we're putting them together. So what I normally do is just graph each one separate, just like you did a second ago. Okay, let me change to red so it matches the color we used before. So I'm going to do the top one in red, just like we did before. So I'm going to get that one graphed just like we have it up there. Okay, so let me go ahead and get it on here. It was strictly greater than, so it was dashed. But what I like to do on these before I do my shading so it doesn't get too messy is rather than showing all that shading, you know, I know that I already tested that 0.21 and it worked. So that side, I'm just going to put some littler arrows for now until I make the final determination, because for this one, I need the points that work on both the first and second equation. Okay. So I like to wait before I put my final answer. All right, then let me do the second equation. This process would take longer if you hadn't already graphed the lines. You know, you'd have to graph the line, 3x minus 2y equals 12, but we have already done that. You'd have to decide about solid versus dashed. It would be solid because it has the or equal to. That one had the or equal to. You would then use a test point, but remember we already tested 0, 0. Okay, and 0, 0 worked, so we were going to shade this way towards 0, 0. It really does help to use different colors or like a pen and a pencil when you're doing systems of inequalities. All right, here's how I want you to think about it. Okay, so do you see the red dashed line and the blue solid line and how they intersect right here? Think of that like scissors, you know, where the scissors are hooked together and you could move those lines independently. And you see how you have these 4 regions? You have, you know, 4 regions. I'm just labeling them. These are not labeled like quadrants or anything. I'm just labeling the regions. See that? There's like 4 regions. Okay, what you need to graph this solution set is you need the points. The solution is going to be the points that work for both inequalities. Okay. So the little small red arrow is pointing somewhere, and then the blue arrows are pointing somewhere, and you need to locate the points that work for both the red line and the blue line. So do you see over in region 3, the blue goes into it over here. The blue goes into it, points into it, see here? but the red doesn't. So it's not there. And see how in equation 4, the arrows are pointing away from it, so it's not there. It's not 1 because red goes in there, but blue doesn't. But you see how region 2, the blue goes into it and the red goes into it? That's what you're looking for, is the region where both sets of arrows are pointing there. That's the solution. And let me change the color because red and blue would make purple. So let me go ahead and keep up that concept. Let me change this to purple. Here's a nice purple. So really the answer to the question, where you would want to fill in, is right here, where those arrows are both pointing into the same region. So the solution would be all the points in there and the points on this part of the line, but not that because it's dashed on the other one and not these. The main thing you have to do is fill in the appropriate region on the Alex problem. Okay? All right, so I'm going to stop the video. That's kind of the overview of 4-5, and then I'll work some more of these in class on Thursday, and then I'll make another video available to help you over the break if you're trying to do it.